Hi, my name is Parag Datta, and I am a PhD candidate in the Department of Computer Science and Automation at the Indian Institute of Science, Bangalore. I will be presenting our ICCV 2025 paper on using Fourier Neural Operators as visual encoders for model-free reinforcement learning. Reinforcement learning is an online active framework for learning, where an agent interacts with the environment. The agent has control over the actions, and the policy to pick actions is based on the environment states or observations. The action influences the environment's transition to the next state, and a feedback is received based on the quality of the agent's action. The observation can be images, and this setting is called visual reinforcement learning, where the agent learns control from partial observations in the form of images. We replace the agent policy by a neural network. We assume that this neural network has two parts: an encoder that converts the images to a representation in the latent space, and a policy pi that samples an action from the action space based on the latent representation. If we have a good enough encoder, we can use our favorite RL algorithm to learn the policy pi. Additionally, since we are using neural networks, we can backpropagate the gradients through the encoder as well and learn both the encoder and the policy end to end. Since 2013, we have been using vanilla convolutional neural networks or CNNs as our go-to image encoder for visual reinforcement learning. Although there have been a lot of architectural progress in the computer vision community, such as VGG and residual networks, these architectures cannot be used as plug-and-play replacement for conventional CNNs because, firstly, reinforcement learning algorithms are very sensitive to hyperparameter changes, and hence, for each architectural change, a new set of hyperparameters need to be searched. Secondly, it is very hard to justify the effort of architectural changes and the corresponding hyperparameter search since the performance gains are often minimal compared to vanilla CNNs. And finally, CNNs have a fatal flaw. They are highly sensitive to not only the training distribution of images but also the size of the input images. Recently, a new class of models called neural operators was introduced by Caltech. Rather than transforming data points, a neural operator maps two function spaces and learns the underlying PDEs from data. The image shows a Fourier neural operator layer where the upper path first transforms the signal into the frequency domain, returns the low frequency signal components, and manipulates them before transforming them back to the signal space. Since high frequency signals often correspond to noise, the upper path can be thought of as capturing the global information in the signal. The lower path is a 1 cross 1 convolution that only attends to local information and adds relevant details back to the signal. This is our proposed architecture. The gray arrow is an up projection layer, the blue blocks are the feature maps, and the blue arrows are the FNO layers. The black arrow denotes a channel-wise max pool operation. So if the number of feature maps was 256, after the max pool operation, the representation vector will be of 256 dimensions, irrespective of the size of the feature maps. Note that the shape of the feature maps being input and output to each layer is the same. And since the CNNs are all 1 cross 1 convolutions, thus the network is independent of the input image size. Finally, the latent representation can be passed through a multilayered perceptron, denoted by red, and trained using a model-free reinforcement learning algorithm. But the question still remains, what advantage does using FNOs provide compared to other architectures? Well, FNOs-based encoders can exploit the underlying PDEs by learning the same, which should lead to faster and more sample-efficient learning. Please note that Markov decision processes or MDPs accommodate stochastic transitions, but we are assuming deterministic transitions, which is true for most environments by and large. Additionally, since we are only modifying the encoder we can replace the CNNs with FNOs for all major classes of model-free reinforcement learning algorithms, namely policy gradient, actor critic, and Q-learning. We also find that no additional hyperparameter search is required for FNOs, and they work well with hyperparameters obtained using CNNs. Finally, since we are essentially learning in infinite dimensions, the model exhibits zero-shot domain adaptation properties in terms of image resolution. During training, rendering of low-resolution images can speed up training time. But during inference, we can use the high-resolution images in Fourier neural operators without any performance degradation. Now we will talk about our experimental setup and associated results to justify our claims that Fourier neural operators are superior to CNNs and other architectures for model-free visual reinforcement learning. We have reported the results of 5 out of 26 games from the Atari 100K benchmark. As can be seen, our results are competitive or better than existing methods. We have used efficient rainbow as our baseline method and replaced the CNN with an FNO based encoder. This modification itself beats efficient rainbow in 20 out of 26 games. Curl uses a contrastive representation learning based technique called momentum contrast to learn better representations on top of efficient rainbow. We achieved 26.1 median human normalized score across 26 games compared to the 16.1 achieved by Curl. This is an ablation to understand what our model is learning. This is the freeway environment where a chicken has to cross the street. The left four images correspond to four sequential time steps, which are given as input to the model. We distill the MLP policy by a single affine layer, and based on the weights of the outputs for the sequence of images, we combine the last feature map. We can see in the last image that the model has somehow learned to predict the future, even though we are not in a model-based setting. It might be a little hard to discern, but if you look at the right hand side edge of the image, notice that the green circle corresponds to the car appearing into the observation space, and the red circle corresponds to a car disappearing from the image in the next step. This is a comparison for the Atari games in the offline setting. We use regularized behavior value estimation as the base method and replace the CNN there. As can be seen, not only are we improving upon the regularized behavior value estimation, but also we are getting better results than all other offline RL methods, including the state-of-the-art methods such as decision transformers, compared to which we achieve close to 3 times the human normalized score. After training the Atari games with Q-learning based methods, we move on to actor-critic methods for the Wisdom Deadly Corridor task. This plot shows that FNOs are more sample efficient and can learn to reach higher rewards faster than vanilla CNNs. Here, we had to take the average of 10 games since the variance was high. Finally, we have plots for the Carla autonomous driving task, where we use PPO as the base algorithm. The plot on the left clearly shows the advantage of using FNOs. The image on the right is an ablation experiment that shows that changing hyperparameters like discount factor and learning rate can actually make the learning worse compared to the default CNN-based hyperparameters. One more interesting phenomena we observed was that using random crops often helps with the overfitting and enables generalization in CNN-based networks, but using random crop is actually bad for FNOs. Next, we also have a few video demonstrations showing the efficacy of our model. In summary, we propose a Fourier neural operator based encoder for model free visual reinforcement learning, which can be seamlessly integrated in place of traditional CNNs with minimal effort. We demonstrate the effectiveness of our proposed encoder on multiple visual environments in both online and offline setting across multiple families of RL algorithms. We additionally try to understand the representations learned and the generalizability of the learned representations through adequate ablation experiments. FNO encoders exhibit a special property of being invariant to the image input resolution and can thus perform zero-shot domain adaptation. Thank you.